Hello students, welcome to video lecture series for the course Data Mining and Data Warehousing. Today we shall learn distance measures that are commonly used for computing the dissimilarity of objects described by numeric attributes. In earlier lecture, we learnt how to compute proximity for nominal and binary attributes. And in today's lecture, we shall quickly revise the term distance and all the axioms which are to be satisfied for calling any distance measure as a metric. And we shall be learning proximity measures for numeric attributes. And typically those are Euclidean distance, Manhattan distance, Minkowski distance. And we shall also learn proximity measure for ordinal attributes. Before we learn what are the distance measures for numeric attributes, let us quickly retouch the topic distance and distance proximity axioms. In earlier videos, we learned that given that we can place our data in the space, how to compute nearness or farness of one point to another point in the space. The concept of nearness or farness in the space is also called as proximity. Proximity is quantified in two ways. One, by computing distance or by computing similarity between any two data points. And these data points we also refer as vectors. Before discussing how to calculate the distance between any two pair of vectors, let us revise the term distance in brief. Distance refers to how far is the data point from the other in space. We have also referred data points as vectors, which are defined with the attributes which we call as features. And we can always compute distance between any two vectors. Dissimilarity measure is maximum when objects share no similar feature values. And dissimilarity measure is minimum when objects share most of the similar feature values. The literature also refers distance and dissimilarity interchangeably. Most of the times it is correct too. Though they are used interchangeably, the distance and dissimilarity have a very minor thin line which differentiates these two. The dissimilarity coefficients are conceptual and mathematical and is inverse of similarity coefficients, that is Dij, that is we have done this. Dissimilarity between any two objects I and j is 1 minus similarity between I and j. Special case of dissimilarity coefficient is a distance. Dissimilarity measures may or may not be metric. Dissimilarity measures are called as distance coefficients if are metric. A distance formula that satisfies proximity axioms is known as metric. So we just discussed that there is a very thin line between dissimilarity and distance. Special case of dissimilarity is distance, and any dissimilarity measure is said to be distance if it satisfies these four properties: non-negativity, identity of discernibility, symmetry, and triangular inequality. A measure that satisfies these conditions is referred as metric. Let's see these properties one by one. Let us learn these distance properties. First one is non-negativity. It says that distance between any two points is going to be non-negative. So if we consider 2 points P1 and P2, then distance between P1 and P2 is going to be always positive, that is greater than or equal to 0. Next property is identity of indiscernibility. It says that distance between any two points is, if it is 0, it means those points are equal. The distance between any object with itself is 0 because every object is exactly same as itself. As they are both similar objects, distance between object with itself results in 0. In other words, we can also say that if distance between any two points, say P1 and P2 is 0, if and only if P1 and P2 are equal. Indiscernible means impossible to see or clearly distinguish between the two. Next property is symmetry. It says that distance between any two points, say P1 and P2, cannot be different than distance between P2 and P1. That is, if we compute distance from any point P1 to P2, then distance from P2 to P1 are not going to be different, they will be equal. So distance between Pi and Pj is equal to distance between Pj and Pi. And the fourth important property is triangular inequality. It says that distance from one point to another point cannot be greater than distance between the same two points via another point. That is, distance between P1 and P2 is always going to be less than or equal to if we travel from P1 to P2 via P3. That is this point. We are traveling. So these are four properties: non-negativity, identity of indiscernibility, symmetry, and triangular inequality. And any dissimilarity measure which satisfy all the four properties is said to be a distance metric. This was all about distance and its properties. Let us learn most popular distance measures which are used for numeric attributes. Given pair of vectors which are nothing but data points or rows of a table, we can use distance measure to compute how different or similar the vectors are. And the most popular three important measures which are used for computing distance between numeric attributes are Euclidean, Manhattan, and Minkowski distance measures. Let us learn these three distance measures. Let us learn initially the distance measure that we are already familiar with from geometry, that is Euclidean distance. Euclidean distance is a straight line distance between any two points in a Euclidean space. In earlier videos, we have defined the terms data point, vector, dimension, space with reference to data mining. When some data object, say x, is defined with n attributes, say x1, x2, x3 like this up to xn, then we say that x is a point or a vector defined with n attributes and number of attributes becomes the dimensions. These x1, x2 are called as coordinates of x. Here, natural number n is called dimension of the space. Euclidean space is a fundamental space of a classical geometry. Originally, it was three-dimensional space of Euclidean geometry. But in modern mathematics, there are Euclidean spaces of any non-negative integer dimensions. The Euclidean distance between any two points P and Q is the length of line segment connecting them, say PQ. As we are computing a length of line segment that connects any two points P and Q with straight line, Euclidean distance is also called as a straight line distance. Let us consider two points A defined with x1, y1 and B with x2, y2, be two data points. The Euclidean distance between these two data points A and B is computed as sum of square difference and taking its square root. So we say that distance between A and B is square root of sum of square difference between the coordinates, that is x2 minus x1 its square plus y2 minus y1 square, and we take its square root. Here in figure we are given 2 points A and B in xy plane defined with A with coordinates x1, y1, B with coordinates x2 and y2. Now how do we compute distance between these 2 points? Mathematically we know that we compute a value of D as root of sum of square differences between coordinates. And we know that this is done with a Pythagoras theorem. So look at this, how we computed using Pythagoras theorem. This source of this formula is Pythagorean theorem. So in figure you can see that this is D, which is whose value is to be computed, and this is right angle triangle whose diagonal it is. So we have to compute value of D using D square is equal to A square plus B square, and then we take square root of to get the value of D. And to find out value of A and B, it is nothing but A is this side, which is computed as y2 minus y1, and B is computed as x2 minus x1. And this is how a Euclidean distance in two-dimensional space D for 2 points A and B defined with coordinates x1, y1 and x2, y2 is computed as square root of sum of square difference of coordinates. Just again, as out of interest, I was reading about this great mathematician Euclid. Euclid, a Greek famous mathematician, was born around 365 before Christ. Though very little is known about his life, it is believed that he was a student of Plato and he was born in Alexandria, Egypt. Euclid's most famous work is his collection of 13 books, which are dealing with geometry, named as the Element. And it is also said that these books are studied the most apart from Bible. Introducing you also about this great mathematician Euclid in brief. Euclidean geometry is study of points, lines, planes and other geometric figures. Most of the proofs he made were by his own. Euclid understood that building a logical and rigorous geometry depends on foundation. A foundation that Euclid began in book 1 with 23 basic definitions, such as a, a point is that which has no parts, and line is length without breadth. In mathematics, the Euclidean distance or Euclidean metric is the ordinary straight line distance between 2 points in Euclidean space. With this distance, Euclidean space becomes a metric space. The associated norm is also called as Euclidean norm. Older literature refers to the metric as Pythagorean metric. Euclidean distance is considered the traditional metric for problems with geometry. It can be simply explained as an ordinary distance between 2 points. It is one of the most popularly used algorithm in cluster analysis, and it is used in formula of K-means algorithm. In data mining sense, the similarity measure is the distance with dimensions describing object features. That means if the distance among 2 points is small, then there is high degree of similarity among these objects, and vice versa is also true. This was brief introduction to this great mathematician Euclid and his work. Coming back to a proximity measure, that is Euclidean distance for numeric attributes. We have just defined that if attribute is numeric, then distance between any 2 points which are defined with these numeric attributes can be computed using this Euclidean distance metric. And how is Euclidean distance between any 2 points computed? It is square root of square difference between every respective 2 features. So let us look at these 2 points x1 and x2 defined with 2 features. x1 defined with feature 1 as 1, feature 2 value as 2. Similarly for x2 values are 3 and 5. Now how do we compute Euclidean distance between these 2 points x1 and x2? We use our formula where we take a square root of sum of square difference between respective features. So we take difference between 1 and 3 first, its square, plus difference between 2 and 5 and its square, and we take a summation of these and then we take its square root. So square root of 13 results as 3.61. This is the simplest example just to understand the formula which we just discussed. The distance between any two points with two features can be computed as this. And here it results that there is a distance between the points x1 and x2 is 3.61. This is another example. This is to find radius of a circle. Given that the center is 2 and minus 3 and point is minus 1, minus 2 lying on the circle. We know that radius is distance between center and any point on circle. Hence, a distance which is to be computed, which is nothing but radius, can be computed using our Euclidean formula. So we substitute values, that is, we take a square difference, we take a summation of them, then we take square root of it, and we get radius as 3.16. These were the examples where we treated them as just points with two coordinates. And in data mining, what we do is we have a table as this, where these are data objects and these are their features. So this is a table where we are given 5 objects and we are given 2 features, and the values of both the features are numeric. That is, both the attributes are numeric. Now, how do we find distance between any two objects? So finding a distance between any two objects is nothing but finding a distance between any two rows using Euclidean distance formula. This is because it is well said, we have defined prior, that this tabular data is forming a Euclidean space. So we use a formula of Euclidean distance and we get that these two rows, say in 2 rows we are treating. We are trying to find out distance between 2 rows, that is row 2 and row 5, which is nothing but object 2 and object 5. So we use these two features, we substitute in Euclidean distance formula and we get distance between, that is, what is a similarity or a distance between object 2 and 5. We compute distance and similarity, as we know that subtracting distance from 1 will give you similarity between any two objects. These were two-dimensional data sets. That is, we had two features. Data point was defined with two coordinates x1, y1. What if we have three features? What if records are defined with three features, say height, weight, email, and mobile number, or something else? And if all the three features are numeric, then our Euclidean distance formula is used for 3 dimensions as this. It is, again we are going to take a square root of sum of square difference of all the coordinates, that is all the features. Look at this example. In this example, we are given again 5 objects and we have 3 features. And now again, if we want to find out a distance between object 2 and 5, we will use Euclidean distance formula to compute it. And that is, distance between object 2 and 5 is computed using Euclidean distance formula by substituting these feature values. And we get that for these 3 features, distance between object 2 and 5 is 6. So we just looked at a table with 2 features. Similarly, we had objects defined with 3 features. Now question is, what if we have a data set with n dimensions, that is, every object defined with n features, feature 1, 2, 3, like this up to feature n. Then this formula of Euclidean is generalized to compute distance between data objects which are defined with n points. So let us consider 2 points A and B defined with features f1, f2, f3, like this up to fn, and g1, g2, g3 up to gn. Now distance between these 2 points A and B with the Euclidean formula is computed as a generalized formula as this. It is same. We are going to take square root of sum of square difference of each two features of these two data points. And this formula can be rewritten as a summation formula where it is square root of sum of Fi minus Fg whole square for I varying from 1 to n. And Euclidean distance, this formula satisfies all four metric properties that we had discussed earlier. This was Euclidean distance metric. Let us learn about Manhattan distance metric. Manhattan distance is usually preferred over more commonly used Euclidean distance when there is high dimensionality in data. Let us see. Look at this figure. We are having 2 points, point A and point B. We want to find out how many are the paths from A to B. We are given third point C also. So if we look at the simple figure, then we have two paths. This is a right angle triangle at point C, and we are having two paths. One is we can traverse from A to B, and the other is we can traverse from A to B via C. So we have two paths. One is A to B shown with red line, and other is from A to B via C shown with blue line. Now what will be distance D? We know how to compute using Euclidean formula. And to compute distance between A to B via C is simple sum of distance from A to C and then from distance from C to B. But what if there is a building like this, and if these were the points connecting at some city areas through road? If from A to C is a road connecting to area C, and from C to B there is another road connecting area C to B, and if we want to traverse from A to B through a red line which we had shown earlier, now shown with a yellow color, if there exists a building of this kind, then we cannot have a traversal as this through car or walking. Then this distance is said to be a real distance, which is Euclidean distance, and a distance from A to B via C is called as Manhattan distance. And this distance between A to B via C is nothing but distance from A to C, that is, and from C to B, that is x2 minus x1 plus y2 minus y1. From this figure you must have noted that Euclidean distance is a straight line distance. We just defined it, and it is also said to be a real distance because if these are the roads connecting and city areas, then when we want to go in straight line, like in Euclidean distance we computed, that is from A to C directly shown as yellow line, then it is a aerial distance. And if you want to go via road, that is from A to B via C, then it is also named as taxi cab distance. Look at this figure. In this figure, these are the middle black one boxes you can consider as buildings or the middle city areas where there is no road, and the white one are the roads. And if we have such a rectangle planned city, then the distance between any 2 points A and B are calculated as x1 minus x2 plus y1 minus y2 and is called absolute distance. These are the absolute differences, and this is called as Manhattan distance. Manhattan's distance is also called as rectilinear distance or snake-like distance, also called as city block distance or taxi cab distance, because this is when taxi travels through a road where there are the buildings at the middle blocks, then it cannot have a straight line distance. It cannot travels like a straight line shown with the green line. It has to traverse using this blue line or similar lines. This is why it is called as block distance. And these horizontal and vertical strips are much similar to one Manhattan area at New York. This is why this distance is named as Manhattan distance. So if we are given two vectors A and B, say defined with two features x1, y1, x2, y2, then Manhattan distance is nothing but sum of absolute differences between these respective features. And Manhattan distance, as we just learnt, is also called as city blocks distance because it is something like traveling from one area to other is like something in terms of blocks, such as 2 blocks down and then 3 blocks right or left or up is summed up as 5 blocks. This is why it is named as city block distance, rectilinear distance, also called as crow flies distance. This simpler absolute difference in every dimension computed without squaring the differences and without taking square roots. It is simple summation of absolute differences of all features. That is, we just sum up differences between any two vectors in all dimensions. That is for every dimension. Let us consider two vectors A and B defined with n features. Then Manhattan distance between A and B is computed as sum of absolute differences between every respective feature. And the most important thing, Manhattan distance is a metric because it satisfies all four axioms which we defined in earlier slides. Look at one example now for Manhattan distance. Again, very simpler one. X1 defined with 1, 2, x2 defined with 3 and 5. And Manhattan distance between these 2 points is just absolute difference between sum of absolute differences of the coordinates. These were earlier were 2 features. Now let's just look at vectors with 4 features. Then Manhattan distance between A and B is computed as taking sum of absolute differences between respective features, and it comes out to be 18 here with 4 features and here it is 5. These were 2 important distance metric we learned, Euclidean and Manhattan. Generalization of Euclidean and Manhattan distances is nothing but Minkowski distance. Let us learn more about it. Minkowski distance is generalization of Manhattan and Euclidean distances. For two vectors, say A and B, defined with n features f1, f2, f3 up to fn for A, g1, g2, g3 up to gn for B, then Minkowski distance between A and B is computed as. It is a generalization of these two. We were taking square root in case of Euclidean, and we can say that first root, that in case of Manhattan distance, no square root, no squares, it was simple difference, summation of absolute differences. Now we are going to compute Manhattan distance with this generalization formula, where we take hth root, of summation of difference of all the features powered to h. That is, we compute difference between all two features, we take its hth power and then we add all these values and then take its hth square. This is also rewritten as this. Minkowski distance, as earlier two distance metrics, satisfies the 4 axioms, that is distance properties, so it is also a metric. So this is the formula which we defined just now to compute Minkowski distance between any two vectors defined with n features. Here h is a real number such that it is always greater than or equal to 1. In some literature, this h is replaced with p and it is called as LP norm. Here, when value of h is 1, then it is a Manhattan distance and it is named as L1 norm. Whenever the value of h is 2, then we call it as Euclidean distance and it is said as L2 norm. And when this h tends to, it is maximum, tends to infinity, then it is called as supremum distance, and it is called as an L infinity norm. And it is also called as Chebyshev distance, that is generalization of Minkowski distance for h is equal to infinity. So in brief, for this formula, generalized formula for Minkowski distance, when value of h is 1, it is L1 norm, value of h is 2, it is L2 norm, and when h tends to infinity, it is said as supremum distance and L infinity norm, and is also named as Chebyshev distance. We just used few terms like L1 norm, L2 norm, supremum distance, that is L infinite norms. These norms are because of this formula which we can rewrite as this. We have rewritten this formula with two vertical bars here on left hand side. The formula is also sometimes written with double bars at left and right. The double bar norms generally indicates L2 norm of vector inside the bars. For h is equal to 1, we can have it is Manhattan distance. For h is equal to 2, it is Euclidean distance. And as h approaches to infinity, it is h norm approaching to infinity, that is maximum norm. And these are nothing but L1, L2 and L infinite norms. H is also represented as P in literature. Please note that H is also represented using P, that is LP norms. So these things which we learned I have listed in a table. When value of h is 1, it is L1 norm, it is Manhattan distance. H is 2, it is Euclidean distance, L2 norm. And when we have L maximum, then it is Minkowski or supremum distance. And these are their formulas. Here you can see that it is subscript 1 when it is L1 norm. It is subscript 2 when it is L2 norm. It is also written with 2, that is double bars on left hand side for indicating distance between A and B. And when it is maximum, H is maximum, then it is supremum distance, that is Minkowski distance, also known as Chebyshev distance, and it is represented as. Let us learn little more about Euclidean norm. In mathematics, a norm is a function from vector space over real or complex numbers to the negative real numbers that satisfies certain properties pertaining to scalability and additivity and takes the value 0 only if input vector is 0. The Euclidean norm or 2 norm, that is L2 norm, is specific norm on a Euclidean vector space that is strongly related to Euclidean distance, and it is also equal to square root of inner product of vector with itself. This was Euclidean norm. Let us solve few examples to compute this Euclidean Manhattan and supreme distance between two data objects x1 and x2 defined with the same values 1, 2 and 3, 5. If you look at this figure, Euclidean distance we learned how to compute. It is computed using square difference between coordinates and its square root. Manhattan distance is simple addition of absolute differences, and supremum distance is calculated as 5 minus 2 is equal to 3. How is this computed now? How did we compute supremum distance? Here we have taken maximum among the differences. Let's look at the formula for computing supremum distance. So before solving some examples based on the topics which we learned today, let us know little more about this great scientist Hermann Minkowski. Hermann Minkowski was a German mathematician and a professor at Zurich. He created and developed the geometry of numbers and used geometrical methods to solve problems in number theory, mathematical physics, and theory of relativity. In Euclidean space, the separation between 2 points is measured by distance between 2 points. In mathematical physics, Minkowski space is a combination of three-dimensional Euclidean space and time into four-dimensional manifold where the space-time interval between any two events is independent of inertial frame of reference in which they are recorded. So this is an example where we are given 4 points and they are defined with 2 attributes each. And we shall be computing Manhattan distance, Euclidean distance and supremum distance for every pair among these 4 points. Let us start with Manhattan distance, that is L1 norm computation. We know that computing Manhattan distance is summation of difference of every attribute for given data points. That is a distance between 2 points. So if we wish to compute distance between x1 and x2, then we have to compute difference between 1 and 3, that is absolute difference, plus 2 and 5. That is going to be a Manhattan distance. So let us table. So this is the table which we have to fill in. In this table, you can notice that horizontal values we have filled in, diagonal values we have filled in with 0. It is because distance between every point with respect to itself is 0. And we shall be computing these values, that is lower triangular values, distance between x2 and x1, then x3 and x1, x4 and x1. Similarly, x2, x3, x2, x4 and finally x3 and x4. So we have to fill in these values. So let us start with, so computation is going to be for x1, x2, it is 3 minus 1 plus 2 minus 5, that is 2 plus 3, that is 5. So this distance between x1 and x2, Manhattan distance is 5. Similarly, between x2 and x3 is 6. And in this way, the way we computed for x1, x2, x2, x3 for Manhattan, we have to compute for remaining and then the values comes out to be as listed in the table. This was for Manhattan distance. Let us compute for Euclidean distance. For Euclidean distance, it is L2 norm. So we have to fill in this table. Again, diagonal values are 0. To compute Euclidean distance between pairs, that is x1, x2, x1, x3 and so on, you know that what we have to do is, we have to take square root of sum of square difference between attributes. So for x1 and x2, the distance between x1 and x2 with respect to Euclidean distance, that is L2 norm, is the square root of 3 minus 1 its square plus 2 minus 5 its square. So square root of 4 plus 9, that is square root of 13, comes out to be 3.61. And computing distance between x1, x2 and similarly between further x1, x3, then x1, x4 and so on can be done using a similar formula and similar calculations, and the values comes out to be as in listed in table. This was for Euclidean distance. Similarly, we can compute supremum distance. How is supremum distance computed? In supremum distance, what we have to do is, we have to take a maximum among the differences. We have to compute maximum among these differences with respect to every attribute. So let us compute for x1, x2. So we are going to take difference of absolute difference of the attributes. Among them, whichever is max, that is supremum distance between x1 and x2. Computing between x1, x3 and then computing similarly the remaining values gives us this kind of values for computation of supremum distance. This was example for us to understand how we are using the formulas which we learned earlier. So this was the input given to us and we calculated Manhattan distance, Euclidean distance and supremum distance. Up till now what we learnt was computing proximity, that is specially distance, for attributes which were of numeric type. Now let us learn how to compute proximity for ordinal attributes. The values of ordinal attributes have meaningful order. We have learnt in first unit the types of attributes where we learnt about this numerical, ordinal and then interval scaled and ratio scaled. The ordinal attributes are the attributes where there is a meaningful ranking and magnitude between any two of these ranks or the order is unknown. Example, some attribute, say size, small, medium, large. It could be something like S, M and L. The cloth sizes, we know that it is S, M, L, XL, double XL and so on. So here there is an order. Small is smaller than medium, medium is smaller than large. They form an order. But we do not know what lies between small and medium. We have learnt about ordinal attributes prior. This is one example. Let the number of possible states that ordinal attribute can have be m. These ordered states define ranking as 1, 2, 3 up to mf. And using these we are going to compute the proximity measure. So suppose f is an attribute from set of an ordinal attribute describing say n objects. The dissimilarity computation with respect to these ordinal attributes is to be used as, so these are the steps which are to be followed. The first step, value of f for ith object is say xif and f has mf ordered states representing the ranks from 1, 2, 3 like this up to mf. We have to replace each xif by corresponding rank. So if say we had a small, medium and large, so we can give ranks as 1, 2, 3 or we can have it 3, 2, 1. You may have it as 5, 6, 7 whatsoever. So we have to replace that state, that is small with 1, medium with 2 and large with 3. Since each ordinal attribute can have different number of states, it is often necessary to map the range of each attribute onto 0 to 1. We have learned in data pre-processing normalization. In normalization, we were mapping the earlier values of attribute to a newer range which was 0 to 1. Similarly, we have to do a mapping of each attribute onto range 0 to 1 so that each attribute has equal weight. We perform such data normalization by replacing the rank RIF of the ith object in fth attribute by using this formula. That formula is written as RIF minus 1 divided by MF minus 1. It is also written in some literature as this. For ith attribute, AI is calculated, new mapped value is calculated as I minus 1 divided by n minus 1. Dissimilarity then is computed by using any of the distance measures for numeric attributes that we learnt earlier using this ZIF for the ith object. So this is one example. We are given a table with 4 data objects and a column 2 is an attribute which is ordinal describing performance in test 2. First object performance is excellent, second is fair and third one is good, fourth one is excellent. And now the steps which we have to follow is we have to count the number of states. So there are 3 number states, fair, good and excellent. So MF value is going to be 3. Now we have to replace each original attribute with its corresponding rank. So resultant table is as this. We are given a rank fair as 1, good to as 2 and excellent as 3. So we are replacing it as this. Excellent with 3, fair with 1, good with 2 and again excellent with 3. Next what we have to do is we have to make observation quantitatively. The values of ordinal attributes are often mapped to successive integers beginning with 0 or 1. Here we have started with 1, 2, 3. You may use different. So next step is we have to normalize these values using our formula ZIF is equal to RIF minus 1 divided by MF minus 1. MF is 3 because we have 3 states. So using this formula we have to now compute normalized value for all the 3, that is good, fair and excellent. So substituting the values here we get normalized value for fair at 0, good as 0.05 and excellent as 1. And we substitute these values here in this table. And now we have to calculate distance metric using say Manhattan distance we can. So these were the values normalized, and now we are computing for each two. That is distance between 2, 1, distance between 3, 1, 4, 1 and so on. And the resultant distance matrix is this. So for ordinal attributes, what we have to do is we have to first calculate number of states. Then we have to map each attribute to corresponding rank. Then using formula, we have to normalize them. Once normalized, any distance measure can be used to compute distance between pair of data points. Now, the last important topic with respect to this proximity measures is when we have tables, when we have data attributes, then they are of variety of types. Say we have a data object student. Then for student we have roll number, permanent registration number, name, email ID, weight, then height, marks, so on. And these are of different types. So one data object is described with number of mixed attribute types. Now how to calculate proximity for such mixed attributes? While learning in initial videos, we have learned that what is a distance, that is proximity, similarity or distance between any two data objects. It is calculated using the individual attributes distance and then computing for data objects. And how to compute individual attributes proximity we have recently learned. How to compute proximity for binary attributes we learned. How to compute for ordinal data we learned. How to compute for numeric data we learned. We have learned for nominal attributes too. Now the question is how to do it for mixed attributes, that is all these types. Previous metric on similarity measures assume that all attributes were of same type. Thus, a general approach is needed to compute proximity for different data attributes. One straightforward approach is to compute similarity between each attribute separately and then combine these attributes using method that results in similarity between 0 to 1. Typically, the overall similarity is defined as average of all individual attributes similarities. So we have learned how to compute proximity for attributes, where attribute types were varying. When we learned for numeric attributes in this video, we learned that there are three measures for computing distance of numeric attributes. One was Manhattan distance, other was Euclidean, third was Minkowski. Now the question is, how do you decide which is the proper proximity measure based on the current data? The type of proximity measure should fit the type of data. And for many types of dense or continuous data, metric distance measures such as Euclidean distance are often used. These are some general observations that may be helpful in deciding which proximity measure to select. These are just few suggestions to adhere to or can be followed. They don't cover all types of existing data sets. Final determination of proximity measure is always a problem dependent. But let us look at some typical measures which are followed. Proximity between continuous attributes is most often expressed in terms of differences, and distance measures provide a well-defined way of combining these differences into overall proximity measure. When data is sparse, it often consists of asymmetric attributes. We typically employ similarity measures that ignore 0-0 matches. Conceptually, this reflects the fact that for a pair of complex objects, similarity depends on number of characteristics they both share rather than number of characteristics they both lack. For such type of data, cosine similarity or Jaccard coefficient is used. We have learned this in second video where we learned proximity measures for binary attributes. And we learned that when we have a symmetric data, then we go for simple matching coefficient. And if data is asymmetric, then we ignore attributes where both the values were 0 and we go for Jaccard coefficient measure. We have learned this. And cosine similarity we shall be learning in next lecture. So these are typically general observations that may be helpful in selecting right proximity measure. So these four we just learned. So summarizing what we learned today is we learned distance measures for numeric attributes. Three we learned: cosine as Euclidean distance, Manhattan distance and Minkowski distance. And one of the popularly used similarity measure is cosine similarity measure that we shall be learning in next video lecture. This was all for the day, and these are the two assignments. Based on what we learned today, you have to solve these assignments and submit. So this was all for the day. Thank you very much. See you in next video lecture.